Hi guys, in this video I will work a few of the comprehensive spec problems. I'll begin by working one that's in the NMR handout. In the Proton Nmr section, we worked the first 3 or 4 of these on a previous video, but the last one, right before the carbon NMR section, I left for you to work. I'll do that one here. It's not entirely comprehensive. It only includes Proton Nmr and IR. It does not include carbon NMR or mass spec. Formula is given. Degrees of unsaturation, C5H12, 2N plus 2, 12, is 0. 0 degrees of unsaturation. That's very powerful information. This compound has no pi bonds and no rings. Since there's no pi bonds, there can't be an aromatic ring. And indeed, if you look at the Proton Nmr, there are no signals for hydrogens on an aromatic ring. Let's take a look at the IR first. Magic line of about 3,000. These peaks are a little bit to the right there, but the magic line I reckon that's 3,000 here. Clearly to the right. That's a little bit. Usually the peaks are right up against the edge there. I don't know what that may mean. Or maybe the tick line is actually right here. Okay, in any event, we got sp3CH typically. Perhaps aldehyde CH? No. This compound cannot have an aldehyde. Carbonyl would be a degree of unsaturation. This formula cannot support a carbonyl. So there's no aldehyde. There's also no peak in the about 8 to 9 region in the Proton Nmr for an aldehyde. No carbonyl. Of course, we would not expect one since there's 0 degrees of unsaturation. There is an oxygen, but there's no OH. So it doesn't appear to be an alcohol. In the end, you know your IR. That was covered in Organic 1. Use your IR information to help tell you about the structure. Okay, Proton Nmr. I mentioned this on one of the previous videos, but this is actually 2 signals here. It's been expanded here. This looks like a triplet. And this is a singlet right beside it. Other signals. Looks like a multiplet, and a triplet. It's been expanded for you here, so you can clearly see triplet. Okay. Integration. Let's maybe look here. Integrals. Boom, 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 boom. These two look the same. This looks a little longer. Let's try millimeters. That's about 1 centimeter. A little bit short of 1 centimeter. But that's almost 1.5 centimeters. It almost looks like 1.5. And this over here, all this is sort of integrated together. We can kind of see the integral line sort of flattening out here a little bit, but then it's continuing to rise. We can just integrate it all together. And what is this? This is about... I wish I had a better ruler here, a smaller ruler, if it mattered. 2.5? Let's see. Well, you can't have half a hydrogen, so is this 2, 2, 3? For a total of 7. And then, but we have 12 total, so if this is 7, that means the remainder would be 5. And indeed, if we multiply this by 2, I'm multiplying everything by 2, and indeed it comes out to 7 and 5, 12 protons. Now all these 12 protons should give signals, and basically they should integrate for 12 protons. So I'm confident that that's my integration. Okay. Now this 5, that's for 2 signals though. It looks like here this is probably 2 and 3 because it's not exactly cut in half. 2 plus 3 equals 5 total. All right. Let's work with these two signals here. Oxygen. Something has moved these signals downfield. These are all sp3CHs, but something has moved it downfield. The carbon that these H's are on, by the way, they are on carbon because there's no OH, there's no oxygen, H on an oxygen. If so, that would be an OH. There's no OH in this molecule. All H's are on carbons. This carbon must be bonded to an oxygen, both of them. Now this is 3H, singlet. That's most likely a CH3. And it's a singlet because there's no neighbor. It's isolated. Isolated CH3. No splitting. So the neighboring atom has no H. Alright. This looks like an OCH3. Then this is likely a CH2. Likely also bonded to that oxygen. But this is a triplet. What would make this a triplet? Well, bonded to another CH2. And so this is a singlet 3H. This is a triplet 2H. Both of these being downfield because they're both bonded to oxygen. Okay. Multiplets usually arise from complex splitting. Clean singlets, doublets, triplets, quartets, those are typically just not complex splitting. So I'm going to look at this triplet. It's integrating for 3. That means it's most likely a CH3. What makes it a triplet? It's bonded to a CH2. And so this would be a triplet 3H. Okay, we're starting to get fragments on the paper here. I have 1, 2, 3, 5 carbons. Well, that's good. The compound has 5 carbons. All right. I have two other signals. Hopefully, these other signals are for the other parts of the fragments that I've put together. That is, if I'm saying there's a CH2 next to the CH3, there's got to be a signal for it. Same goes for that. Now, very importantly, we have all fragments on the paper. These fragments add up to C5H12O. That means everything is here, and all we have to do is put the fragments together. And there's only one way to put the fragments together. That is basically hook them together right here. And that's your answer. And I'll do it line bond. We have a methyl to oxygen, CH2, 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 CH3, CH2, 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 CH3. This is our answer. Now, in most all of my problems that I give you, you'll be asked to then label your structure with peak assignments. A couple of different ways to do this. I sort of did that here. But what would we expect here? Triplet 2H. Singlet 3H. And indeed, that's what we have. Both downfield because bonded to oxygen. One on the end here would be triplet 3H. And indeed, we have that signal here. And it's the most upfield, furthest away from oxygen. The other two is 2H. But what would this signal be in terms of splitting? Complex splitting. Splitting from both sides. This is going to be a multiplet 2H. And multiplet 2H. And indeed, there are your two multiplet 2H's. It'll be cleaner to label these with arrows if we had more room here, or using letters. And we may do that on the next example. Okay, does this structure fit degrees of unsaturation? Sure. There's 0 degrees of unsaturation. Does it fit the IR? Sure. There's no OH, there's no carbonyl. The only thing you would expect for this compound is sp3CH, and indeed that's mostly all that we have. The remainder being fingerprint. Okay. Good. I'm now going to do the more comprehensive spec problem that was in the pre-course worksheet assignment. Now, I've sent the key to this out already, but I'll work it here, and I'll go through it. Based on the spectral data provided below and the information in this paragraph, determine the structure of the unknown compound. Molecular formula is given. This compound gives a positive Jones oxidation test. Right here, what is the meaning of that chemical test? Positive Jones. That means that this compound can be oxidized. Compound can be oxidized. If an alcohol, it's primary or secondary. Now you could just say it's primary or secondary alcohol, but you have to be a little careful there because other things could give a positive Jones. Now, is this compound an alcohol? contains oxygen in the formula? Yes. Look in the IR. Looks like it could be an alcohol. Let's do degrees of unsaturation. C9H12, 2N plus 2 would be 20. We're missing 8, 4 degrees of unsaturation. Useful information. IR. 4 DUS. I'm going to look here real quick though. I see aromatic protons. Looks like an aromatic ring. The most common aromatic ring is a benzene ring. We also have signals for aromatic carbons in the carbon NMR. This looks like it contains a benzene ring. Thus, the 4-DUS is solely for the benzene ring. That means there cannot be a carbonyl. Indeed, this signal is about 1613. That's not a carbonyl. No carbonyl. You cannot have a carbonyl and a benzene ring in this formula. Let's see here. sp3CH, sp2CH. I don't think this is much to be concerned about here. Okay, let's look at the Proton Nmr. D2O exchangeable. If you remember, that's a clear indication that the signal is coming from an OH or NH, because OHs or NHs will be D2O exchangeable. We know we have an OH based on IR. This just confirms that. This is your OH signal. Confirm that. Okay. I would look at the aromatic. How many H's on the aromatic ring? 4 aromatic H's. That means the benzene ring has 2 substituents. Very importantly though, this is a pair of doublets. And this most likely indicates it's para-substituted. And so we can have this fragment here a para-substituted benzene ring. 2 signals. You would expect 2 signals here. Assuming the substituents are different. The H here and here are the same. The H here and here are the same. 2H, 2H. Doublet. That's a doublet split by this H. This is a doublet split by that H. Classical pair of doublets typically indicates a para-substituted isomer, as opposed to a meta or ortho. Okay. These signals are moved downfield some. Singlet 2H. This is going to be an isolated CH2. I know it's isolated, meaning there's no splitting. There's no H's adjacent, because it's a singlet. Quartet 2H. That's a CH2, most likely. Why is it a quartet? It must be bonded to a CH3. Being bonded to a CH3 makes this a quartet. Now, if we're going to say there's a CH3 here, there must be a signal in the H-NMR for the CH3. And indeed, our last signal is a 3H signal. It's a triplet. And indeed, the CH3 here would be a triplet because it's bonded to a CH2. 2 plus 1 is 3, triplet. So this is the CH3. And this here, quartet triplet, with often the quartet maybe being downfield some, because the CH2 is bonded to something electronegative, perhaps, or maybe to a carbonyl or something. But a quartet triplet is a classical pattern for an ethyl, okay? As shown there. Now, that excludes the singlet there, of course. Quartet triplet, classical ethyl. We have an OH, we have an isolated CH2, and we have a para-substituted benzene ring. Do we have everything on the paper now? Formula C9, 6, 7, 8, 9. Yes. 2 oxygens. Well, hold on. We only have 1 oxygen here. We need another oxygen. 12 H's, 4, 5 makes 9, 2 makes 11, and the OH makes 12. All of our H's are accounted for. Okay, fragments. Ethyl. Now what it cannot be is put the ethyl on one end and the OH on the other. That cannot be the answer because this is not formula, and you have no other place to put fragments. All valences are now filled. You cannot make any more bonds to these atoms. So let's don't go there. These two groups are both downfield, likely bonded to oxygen. So I'm actually going to put an oxygen here. And maybe the other one is bonded to oxygen as well. Well, maybe this is the OH. And now we can put fragments together. One side being the O-ethyl fragment and the other side being the CH2 OH fragment. Uh, 4 degrees of unsaturation, correct formula. This would be oxidized by the Jones. This would give a positive Jones oxidation test. Okay. We'll see if we can confirm this. Let's make assignments here. Let's confirm it first. Could it be some other structure? We got to keep the ethyl together. What about this structure? What if we put the ethyl there, maybe the oxygen here, isolated CH2, and then the OH? This is not the structure because our quartet is way downfield. Got to be bonded to oxygen. This quartet would be about 2 to 3 ppm. benzylic, it would not be 4 ppm. Also, this CH2 would be a singlet. By the way, we need to point something out here. But this guy being bonded to 2 oxygens, this would be like about 5 or 6 ppm. Doubly downfilled. I don't think this is the answer. And I also know that this is not a stable functional group here, this carbon with these 2 oxygens like that. No. This is just structure. It seems like I was trying to see if there's any other possibility. I don't think so. Okay, let's make assignments here. Here's our answer. Assignments here, I'll do... I'm going to label these as A, B, C, D, E, F, and G. Okay, I'm giving you coupling here. Singlets. These would be singlets if coupling was, if this was a coupled spectrum. These 2 are singlets. That's these 2 guys. Singlets mean there's no H there. There would be no splitting with coupling. Those are also short peaks. Okay, and that makes sense too. C and D. Now see, I don't know which is which. I don't know which is C or D. I don't have to be that definitive or precise. One of these is A, one of those is B. One of these is C, one of these is D. Same thing with the 2 triplets. That's going to be a triplet, and that's going to be a triplet in the carbon NMR if we had splitting. Why am I doing that? Should be using letters. E or triplet, and well, see, EF, EF. I don't know which is which. They're so close you can't hardly distinguish them. One of these is E, one of these is F. G would be the one furthest away from oxygen, most upfilled. If we had splitting, that carbon would be a quartet. Okay. Show the structure of a likely ion that would form in the mass spec of this compound. We could do a alpha cleavage on the near the ether oxygen, and we could leave behind that carbocation. We could show a resonance structure if we would like. This is M-15. So that ion is quite likely in the mass spec. Okay, that took a little time, but I did a lot of discussion, all right? With practice, you should be able to put these together quicker and quicker. Now notice, I came up with structure. I didn't even use carbon NMR to come up with structure. I just only assign peaks in the carbon NMR, as usually the instructions will require you to do. Okay, let's try another. This is page 15 in the workbook. I will do this one, the first of several comprehensive spec problems. Now the answer key to this is in the book, in the workbook, but I'll go through of how I would work these problems, or this problem. Okay, formula is given. X is halogen, so it's some halogen, but we have to figure out what the halogen is. Let's see, DUS. X halogen counts as an H, so that's 14, 22, it's missing 8, 4 DUS. IR sort of has the sp2CH, sp3CH. This looks like an aromatic signature. Looks like it has an aromatic ring. The formula supports a benzene ring. We have aromatic signals in the carbon NMR. We have aromatic protons in the proton NMR. Looks like a benzene ring. Thus, if it is a benzene ring, that's your 4 DUS. That means there's no additional pi bonds or rings. So this compound cannot have an alkene or a carbonyl, etc. We know it don't have a carbonyl anyway since there's no oxygen. Okay, I see 5 aromatic H's. That means it's a monosubstituted benzene ring. We don't have to worry about isomers. 5 aromatic H's. Only one substituent on the benzene ring. Singlet 2H, CH2, isolated. There's no splitting. We cannot have CH's next door. By the way, I forgot to mention something over here. I don't know if we've mentioned this before. Singlet 2H. Importantly, OHs typically do not split CH signals. So even though this hydrogen is within 3 sigma bonds of these H's here, this H is not splitting this. The presence of an oxygen between the H, that H and the other H's greatly diminishes the splitting or the coupling. And you usually do not see splitting from an OH. There are some cases where you can, but most of the ones we will see no splitting by OHs. Didn't point that out over there. Okay, isolated CH2. Downfield though. Something is moving this CH2 downfield. I'm thinking it might be that halogen. Likely bonded to the halogen. Singlet 6H. What is that, a CH6? No. This is likely due to symmetry. This is likely 2 CH3s. Okay? 2 identical CH3s. Okay, do we have everything on the page here? We got 6 carbons, 7, 8, 9. We only have 9 carbons. This compound has 10. 5, 6, 7. We have 13 H's here. We've got the X. We're missing a carbon. That carbon must not have a hydrogen. Must not have a hydrogen. It's just a lone carbon. Okay, let's look at fragments here. If you put either one of these fragments onto this benzene ring, you're going to be in trouble. we just put the CH2 and then the X, we have no room for anything else. If we just put a CH3, well, we're doubly in trouble because we need two identical CH3s. We have nowhere else to put anything. It must be that long carbon that's bonded to the benzene ring. Now we need three other bonds to this carbon. We have three other fragments. We can put the CH2X here, and we can put the three CH3s. I'm sorry, two CH3s. And these are identical. And there's your answer. We had to recognize that we were missing a carbon there. Okay. Using arrows or letters or sign each signal in the proton NMR or carbon NMR. Five aromatic hydrogens on the ring. This is spelled out enough that we maybe don't need to use arrows. It's very clear that this signal is the CH2 here. I could draw an arrow, but I risk cluttering up my page here. And then the two identical methyls here. Again, I was actually able to solve the structure just from proton and IR. Didn't even use carbon NMR. That's just my approach. We need to assign carbon NMR though. I'll do this line bond. Oh, by the way, what is X? We're going to have to look in the mass spec. The mass spec shows a molecular ion peak at 168. Is that 168? Hard to see here. Well, I'm going to keep this X for a minute here. 119. That is loss of it's got to be 168. What's the difference here? (168) minus 119 equals 49. Minus 49. That's an odd mass. 119. I'm going to look to form a benzylic carbocation. If I lose 15, no, that's not enough of a loss. Must be cleavage here. I cleave there, I'm going to get that benzylic carbocation, and this is 90. Let's see here. That's 119. It's got to be. There's the mass spec. Base peak. Cleavage to give a benzylic cation. We must be cleaving 49 here. X thus must be, the CH2 would be, let's see, minus 14 equals 35. X equals 35, X equals chlorine. We're cleaving the chlorine and CH2 group. Minus CH2 chlorine. All we need here is complete structure for the fragment. That's what we need. Anything else? Just discussion. We need to assign carbon NMR. Singlet would be this guy here. Short peak, it's also a singlet because there's no H. These three signals are the remainder of the ring. Boom, boom, boom. I don't know which is which. Each carbon would be a doublet if we had splitting, because each carbon has one H. Triplet. It's a CH2. Singlet, that means there's no H. There's our quaternary carbon. Quaternary carbon, it has no H. That's why we sort of didn't see a signal in the proton NMR. But here's the signal in the carbon NMR for the quaternary carbon. And indeed, even if we had splitting, it would be a singlet because there's no H on that carbon. S can also stand for short peak. Quartet. Quartet would be here and here. Those quartets are the same. It's the same signal. Perhaps it's really for two carbons. So that's why that signal may be taller than, for example, the triplet. But it's not much taller. Okay. As long as you clearly identify signals, either with letters like I did on the previous one or here with arrows. I can tell structure. I'll redraw it. We got a benzene ring with chlorine and two methyls here. Fits the IR. Mass spec, we have benzylic cation 119. We assigned all of our carbon signals. Everything looks good. By the way, this is interesting to note. We didn't have to consider this. The carbon closer to the benzene ring is not the one most downfield. Well, that makes sense. Sorry. That makes sense. What makes sense is the carbon bonded to the halogen, the carbon bonded to the halogen is the one most downfield. Then the one bonded to the benzene ring is next, and then the two methyls further away from the benzene ring and the halogen are, that signal is most upfield. Okay. Again, in me working these problems, I did take a little time for discussion. Again, with practice and strategy. And hopefully in me working some of these problems, you kind of see some of the strategy that I employ. Okay, guys. There's several problems remaining in the workbook. For practice.